Great. Okay, so folks, I want to thank you, those who have made it in this morning. I did want to note, per my comments, that there's a career fair going on over in Spinks, and I'd like to encourage students to attend that. Because of that, in my classes, I'm making extra efforts to make sure that they are properly recorded, that the audio comes through properly, which is sometimes an issue. And we'll acknowledge if students do want to go over to Spinks, they're welcome to do so. Try to make sure that that the comments and so on are captured properly. I did post a set of items to the class, again per my email. Those items included an updated version of the syllabus with a little bit more information on the marking options, a bit of clarification on team size. It included the first part of the exploratory topic hand-ins, setting up that area, but most importantly right now it has terms of reference and ideas for the first turn, for projects in general and for the first turn-in. Okay, so if you go take a look at that, there's a set of ideas for possible project areas. Those are not exhaustive, but they give some sense as to what appropriate projects might look like for this class, with the particular focus being, because all graduate students have to undertake projects, graduate exploration, but they'd also be suitable for undergraduates who are really, really interested in pursuing a project. And further did some other posts. So today's discussion, I'd like to build on that exploratory, the take-home exercise that I posted, where I gave you some code that is well below my quality standards, but is certainly not unheard of. It's less common in industry teams where that sort of code would be unacceptable, but it's more common than you think in IT shops, in single-person operations, and certainly amongst students. So I provided you some of that code for your thought, and I'm going to, per my comments, provide a refactoring of that code base. And I'd like to solicit from the class here, before I show you my solutions, I'd like to solicit suggestions about how you would go about cleaning up the code. It's my intention to show this code, and the lights up here in the front are a bit too bright. So might someone be able to get the backlights turned down there? Yeah, that's, excuse me, the front lights turned on. The backlights retained. Yeah. Okay, so here's some code. It's not a huge amount of code. Here it's about 70 lines, right? Not a massive code base by any means. Where it really gets hairy is when you have multiple files, each of which is confusing, and they somehow work together. Give me some understanding of some things that are problematic about this code. You struggled with it, presumably. What are some of the things that gave you grief?
It's a 1D array for some weird reason.
Okay, good. So these are 1D arrays? Yeah. For
2D
even though functionally they are 2D arrays, they've been flattened into a single dimension. And this 10,000, where does that come from?
100 times 100.
100 times 100. It's the number of columns and number of rows, multiplication of those two, and that's that 10,000. But the logical connection between that and these hundreds down here is not entirely obvious. And you might be wondering, why is that 10,000, why is that 100,000? And think that, well, this should be somehow related, but this is actually independent logically of that. What is this, 100,000?
Just the steps.
Number of steps, which, it could be 1, it could be 100 million.
It can't be 1, it has to be even. has
Yes,
to be
it does
an
have to
even
be even because the output occurs
On
from
A.
a certain array. Okay, good. Where's that logical constraint captured? It's not. It's merely implicit here. If you made this one, quite right, the information that it outputs down here would be not capturing any steps at all. It would be the original output, because that A hasn't yet been updated. So what's happening? What's going on with these A and B arrays?
You can't update live as you scan because you'll be changing north as you move south.
Okay, yeah, so you'll be changing the cells out from under you, and what we want is a lockstep update, so the current situation here in terms of cells that live different places, the updates to a given cell should depend on the current state. Mind my words there. The current state of its neighbors. Okay? If that state is, if the state of other cells is being modified as you do the update, that's going to be a problem, because it's, in some of these it's going to be depending on the current state, and some it's going to be depending on the future state, which is not what you want. You don't want this artificial kind of entangling of the updates. And so what goes on in order to accomplish this, in order to allow for an update of the state that depends only on the current state, but we use that to create the future state, we basically have two arrays. We have one that's kind of the current one, and one that's the future one. Now, which is current and which is future functionally, in terms of how these things function, varies over time. To wit, sometimes A is the current one, and we're updating B. Sometimes B is the current one, and we're updating A. But we need two arrays in order to accomplish this, kind of like double buffering. And here, we've called them somewhat, well, without a lot of clarity, A and B, and then they end up being used down here in the code. Where's the code that sort of differentiates? Should we be updating A or should we be updating B?
Mod 2.
Yeah, this thing. If I mod 2 is, what is that really testing? Is it? Yeah. It's functionally is that I is odd, but you may be wondering, like, what does this return? I mod 2. What sort of thing is I? It's an int, right? It's a type. Its type is int. So I mod 2 is a what?
It's an integer that
It's an integer that is being treated as a Boolean.
And the fun thing is that 0 is false, so it's going to start on the else.
Yeah. So, yes, exactly. So it's starting on the else case where we're updating B. And that's a bit of a sleight of hand here, but it's a quite common one for certain sub-community of C developers. And so here are the two cases. Here were the current states in A. There are the current states in B. What else was challenging about this code, or what else bothered you about this code?
One of the things that bothered me was that the indexes that you're specifying here are not clear. Like, you can't, at first glance, you're not able to understand which indexes are you actually accessing. Is it northeast? Is it north-south? So it would be a good idea if you can actually define with an easy named variable which index you're working with logically.
Good. So the indices you're talking about are associated with these computations here, right? These you're looking into what's conceptually a 2D array. It happens for implementation reasons that are obscure to have been flattened into a single D array, and now we're accessing into it using some formulas that reflect the fact that there's this flattening going on, but in an obscure way. So we've got A and B. What is A?
Number of columns?
Yeah.
It's the row
yeah, row and then column. Depending whether you view it as a column major order or row major order. In this case, one is being used as the major and the other is being used as the minor. But yeah, I prefer to think of it as sort of row as A and then B as column. But what's this multiplication for? Why 100 here?
Because every 100 is one row.
Yeah, every 100 is one. What about this 99 or 101?
I believe that has to do with southeast and southwest.
Yeah, so here we need some consideration of the fact that we have 100 per row, and here we're looking southeast, and so we've got to go up a row which has 100 items in it, and then we've got to go left one more. So it's minus 100 plus 1, where the 100 is logically the number of items per row, but that connection is lost. It's 101. This is 99 northeast, right? And similarly for these other formula. What's this B less than 99?
You don't want to try access something outside of the array.
Yeah, you don't want to access something outside of the array. So logically, this 99 is associated with the count of the number of rows or columns there. Yeah, columns. And similarly, this greater than 0 is associated with having a special case for the top for the left-hand side, because on the left-hand side we have a different situation going on if we're in the far left row in terms of how we index it. Okay, and so only if we're in the leftmost column, we don't actually need to compute the number of items to our left, either northwest, west, or southwest, etc. Okay, what's this C plus equals stuff?
That's
Count.
the count of the neighbors.
That's the count. And here we're kind of brutally enumerating. Kind of a bludgeon type of count. We're brutally enumerating all these different possibilities. Okay, so what I'm trying to get at here is there's some meaning behind this. There's some semantics. There's some logic behind it, but the logic is obscure. And it's obscured by implementation details, like it's all being flattened into one array. The underlying meaning is being obscured by that. It's almost like these minutiae, these little welter of details that happen to be the case because we flattened the way, have gotten in the way of understanding the logical meaning of what's going on. And that's been, insult has been added to injury by the fact that we're using these obscure variable names, and we're mixing up this code, which involves things like A and B with I, without really having a clear understanding from the names of what those are. What else is kind of problematic about this code?
There are no functions.
There are no functions. Okay, now why is that a problem?
Because you could reuse about 5 of them.
Yeah,
if you
so
had them.
you could have functions that could be fruitfully reused. Okay. What other motivations would there be for adding functions to capture some of this functionality?
You could read main.
I'm sorry. You could basically read what's going on. Okay, good. The logical flow of it would be clear, right? We read some stuff from a file, we go through a bunch of steps, and then we output some stuff, the results of those early steps. So at least that logical flow would be clearer instead of being submerged in all these sort of little distractions. What else benefit would come by breaking it out as a function, things out as a function?
We can reuse it with different parameters, like instead of, we've got the same code copied except A and B
Okay.
switched, right?
Okay, good. So we could parameterize it. We could get some generality by passing in parameters for it rather than in the most brutal way. You know, this is really heinous. I mean, you know, you've got basically the same logical structure. It's just that here you have A and here you have B and here you have A, right? I mean, to me that makes my stomach turn. I mean, when I see that, especially because I look at them and I think it's basically the same, but I don't know. And to figure out, I have to go study it. Like, is anything different here than there? Imagine if the spacing is different and that starts to distract. I mean, it just gets really obscure. Is this basically the same or is it different? Ladies and gentlemen, we should have code that if two things are basically slight variants of each other, it's only a detail change, the code should be written in a way that highlights the one detail that changes, but otherwise reuses the same basic mechanism. So we know, look, it's the same thing, just with this one salient detail changed, right? The salient detail here being which array is being used to collect the information, which array is being written, to which we're writing. We should be able to have an expression of this logic which boils it down so that it's clear here we're counting and updating, and all that's changing is, in one case, we're counting in B, updating A, the other, we're counting in A, updating B. Otherwise, it should be, captured here that it's the same basic operation. But here, we're forced, in order to figure out kind of what's going on and are these the same, to look at all this cruft. This is cruft, ladies and gentlemen. It's just crufty. It's just there's all this stuff standing in the way of the theological meaning of it. Okay, so that's bad. What else is problematic here?
Magic numbers everywhere.
Magic numbers all around. I mean, it would make Merlin blush. You've got these magic numbers scattered throughout 100,000, 10,000, 101, 99, and you go to update, let's say, the number of rows, and you've got to figure out which of these are logically connected with the number of rows and which are connected with the number of columns, what should be updated, how should it be updated, and you can easily make a mistake. But I forgot one other thing I want to emphasize. So back to this issue of breaking it into functions. What's another thing we could do with functions broken out that we can't do here? Or actually, there's several other things. I don't want to lose track of them.
We could reuse the logic between the else statements, if and else.
Okay, yep, and I think that's what Janelle was referring to before. We're capturing the essential commonality of this. But there's a few other things you can do with functions. You can stub them. What do I mean by that? Or what these days we would call more mock them. But what would I do with that?
You
Uh-huh.
write all the functions and then finish doing main without actually changing anything.
Yeah, exactly. So we could have a version of this code which, instead of writing to a file, for example, just tests that the total of the cells in there matches some expectation from our testing database. For the given input, the output is consistent with what we expect from the database, or the count of cells live is equal to a number that we read from the database. So we can have sort of temporary versions of pieces of this, like the thing to read in, the thing to write out, that for the sake of testing, they do different things. And that brings up the broad issue of testing. If I broke this up into pieces, I would argue that I could test it a lot easier. Here, to test the thing, I basically need to feed in files and look at what's written out. And if something's wrong in here, that will eventually allow me to test it, to chase it down. But it could be wrong in a lot of different places here. Maybe it's just the file read function that's broken. Maybe it's writing it out that's broken. Maybe it's something in the logic to update it is broken. Maybe it's something about how it's read. And there's a lot of places it could go wrong. Why does it help if I broke this up into nice functions? Yeah, why is it easier to test? Let's just take that to a very concrete level. So suppose I had 10 functions that captured this code, different aspects of it. Why would that be easier?
You can do unit testing with each of them, like
I could unit test each of those functions. Each has a job in life that's very simple, a simple responsibility, and each would be amenable to tests that would test the logic without testing the whole hairball, without testing the whole enchilada, without testing, ladies and gentlemen, the big kahuna. Okay, so here breaking it up into pieces is gonna help testing. But what else got your goat? What else troubled you? Yes.
I think every time we're looking at index, that's when A is used and it's multiplied by 100. So I'd rather just increment A by 100 each time rather than having to multiply it by 100.
Yeah. Okay. Right. So a lot of unnecessary computation going on here. You're multiplying by 100. A good compiler will look for opportunities to eliminate that. But you could, if you have to do that, you could do it in a lot more efficient way. So I saw the hand up here. I'll go sort of diagonal. Yeah.
So, kind of two things.
Yeah.
First, you could probably parameterize
Yeah.
the width and height.
With a width and height. Yeah.
Yeah, that also makes it so you can easily change if you want the program to make bigger or smaller boards.
Right.
Much easier. And then you could also, that can also simplify all the stuff down there. So like negative 101,
Yeah.
you could probably just times the row by one more than say minus one.
Mhm.
And because immediately, obviously, you're talking about the row before or the row after.
Good. I like that. Those are, and that generality, we have to remember, ladies and gentlemen, that again, much of our goal in software engineering is to make us less vulnerable to unneeded work in the event of changed requirements. The world is changing fast, in case you haven't noticed. In my lifetime, we've gone from stone tools to, well, no, I mean, the truth is, we've gone a long way. And in your time here at the university, new technologies have cropped up. Requirements in business side change a lot. And if we anticipate certain areas of likely changing or possible changing in our program, it behooves us to put in place mechanisms that will allow that area to change easily. Flexibility has value. Flexibility in code has value. That's acknowledged in the business side by the theory of real options, etc. That the ability to change things to respond to changing conditions really has value. And at a practical level, as a software engineer, it means a lot less cognitive overhead, a lot less worry, a lot less stress if things change. And so abstracting out height and width so that they could change easily without us changing the code, that's kind of obvious thing you can almost get for free by abstracting those out. And so that's generally a good thing. In general, when you are creating code like this, you want to be asking yourself, like, which things are likely to change, and for larger investments that will help you dictate, okay, can I just capture this by baking it in, or do I need to do it in a way that's more general? Do I need to do it in a way that has flexibility? There's a principle in agile programming called the Agony principle. Does anyone know that principle? Agony? Yeah, ain't gonna need it. And the idea there is you don't bake in extra functionality. You ain't gonna need it. Okay? And the idea is you don't bake in a lot of additional functionality in a speculative way. Instead, you iterate, once every 1 or 2 weeks with your stakeholder, and if they need it, you add it in. But from principles of design and architecture, often you want to at first think about where's this likely to go, so you don't end up being totally broadsided by a change request and you have to rewrite, a large part of the thing. So there's another hand up in the center. Yeah.
I didn't like the hard-coded input file because you have to recompile in between changing inputs, which I really like.
Yeah. So So you want to change this to, input 2 or, box or whatever, and you got to go change it here. I mean, that's gratuitous. It's again something that's pretty ugly. What would be a much more robust within the C language context? What would be a very common but easier, much more flexible way to do this?
String arguments.
Yeah, command line argument, right. Another hand up over here. Yeah.
That indentation is something else.
Yeah. So again, I've seen worse, but this is pretty bad. This
It's
is
easy to fix though. You paste it into an IDE and it auto fixes the entire program. Step 1.
good. Yeah. So these days it's pretty easy to fix. And even when I was a youth, we had lint or things to spot stylistic issues, and we had pretty printers that would prettify the code. Somehow the prettification was lost to my personal appearance, but that's okay. Okay, so ladies and gentlemen, this indentation is for the birds. It's really bad. In fact, I think even the birds would reject it. So the logical structure is not obvious through the indentation. We have these blocks of code here. We have things that are logically subsumed in conditions that are placed on the same line, which is not itself incredibly objectionable, but when combined with the fact that these blocks are right under the associated condition, it's pretty bad. And then you get areas down here where this is shown visually at the same level as this, even though it's logically subservient to it, even though this is only iterated on based on these conditions. So that can be really misleading, and there are times where that can really bite you because we come to count on these things intuitively. Conventions matter because they let us coordinate. They help eliminate extra work by allowing us to just glance at something and know basically what's intended. And when people don't adhere to conventions like indentation that are cherished and very widespread, it can lead to big problems. This is an example right here of a problem just waiting to happen. You look at this and you say, here we're getting a character from this file here, and you'll note that this is logically subsumed in this if, but it's not obvious that it is. So you might glance at this, think this always happens, but it actually only happens under those conditions. So this is an accident waiting to happen. Or it's a bug that's that much harder to find because you don't realize that this is conditionally executed. And some of the worst types of most frustrating types of debugging are when it's staring you in the face, but it is not obvious because of your assumptions. The fact that you assume, it could never be that, and it ends up eluding you for a while. Okay, so this code is bad. And we've talked about a number of the reasons it's bad. So we've talked also about some remedies. Abstracting out variables, having these things indexed as two-dimensional arrays. What other things could be done to improve this? Putting some functions in place. What other things?
Open and close or read and write function.
Okay, open and close, read and write.
Maybe considering memory allocation because some of
Yeah, okay. So this memory it's going to take a fair bit of memory here, although 10,000 integers is going to be smaller. I would argue this is extremely wasteful, actually. 10,000 integers. Why is that wasteful? Why is that wasteful? What is each integer encoding?
A single bit.
It's a single bit, logically. Is it occupied or not? And here we have this integer to encode that. You can have a boolean. You can have a bit
Booleans in C
vector.
are just integers.
You
though.
can have a bit in C, yeah. And you can have a bit vector that basically each bit, 1 or 0, encodes whether or not it's occupied. And, an int, depending on platform, C allows platforms to differ in this, it's going to be 16 or 32 bits. And it could pack a lot more information in. So that memory allocation, that's a significant, that could be a significant thing as you get to larger grids. What other things could we do to improve this?
The step printing, you could use a debug statement on it.
Yeah, okay, we could have it, instead of always printing it out, for example, we could use logging functionality where if the logging level is such that you want it, it can be included, otherwise you omit it. So you don't always see it. Or you change the frequency of printing, right? How frequently you print. Other things. Yeah.
Go and redeclare your variables over and over.
Yeah, okay. So redeclaration of variables, I don't see a lot of problems here with it. Declaring variables is also something that tends to be fairly lightweight, but what you don't want, and maybe you're getting at this, is variables that live unnecessarily long, that are logically limited to one area, but they live for a lot longer. They have long lifespans. And in here, there may be cases of that. Well, here's, a declaration of C, but C does live basically only in these two blocks. You could declare it separately in each one in order to have it clear that those two are unconnected. But I'm not sure in this code that's as big an issue as it is in some where we have really long variable lifespans. Like this suggestion, though. Others? Okay, so let me show you what I did, and this is not particularly privileged, but here's an example solution. Okay, now I made use of some C time-honored sort of C ways of doing things. These don't always accord with my foremost aesthetic practices, but conventions are important. So first of all, I put a bunch of function declarations, not definitions, but declarations up front. These are, the methods, the functions within this. Now, by convention, it would have been better if I had this in a separate file, a .h file, which I could include and which others could include. But in this case, it was a single project, project with a single file, and I didn't see a need to do that, and I wanted to be able to provide you one file. You'll notice up top I do pound defines of these things, and I put them in parentheses. Why put them in parentheses? There are times where that's a really good, or it's even more notable here. Cell count, and I put in parentheses. Why parentheses?
C macros are weird.
Yes, C macros are weird. It can change precedence. Okay, ladies and gentlemen, this would be particularly an issue if this were a plus. Because if you had cell count times something else, and this were a plus, it would actually turn it into this plus that times something, unless you had parentheses around it. And so in C, generally speaking, we like to put parentheses around things to avoid macro substitution, which is purely literal. It's literally stuffing in, this string into the code. If we don't have parentheses around, it can lead to weird precedence mistakes. So again, if this were this plus this, and then you substitute into something that at times 10, it would only be this plus this times 10, without the parens. With the parens, it prevents it from happening. I don't think it's needed up here, but I put it in for good measure. I typed int to be used as bool. So if I use bool, secretly it's an int. And that allows me to indicate in some things if they return, oh my gosh, I have fallen. How I have fallen. Okay, is legal coordinate correctly uses bool, but is legal textual encoding? Man, bool. Okay, bool, ladies and gentlemen. Is legal textual encoding. Here we go. This should be a bool. Oh, bool. Why am I mean, so logically this returns a Boolean, and this allows me to use bool, say it returns a Boolean, even though secretly it's an integer, the meaning, the semantics of it, that it returns a Boolean instead of just some old int, is important. I want to be able to look at that and say, yeah.
Why didn't you just include standard bool?
I could, but I didn't want to assume use of that, and I wanted to be able to show it directly. You're absolutely right. I mean, there's all sorts of C libraries which could be fruitfully leveraged here, but my point here is not to ask students to master those libraries. My point is to show specific, concrete ways in which this can be enhanced. But C libraries have an admirable set of resources these days for a broader set of types and type encoding that's independent of machine assumptions, etc. Okay, what are the things that I did? Well, you can see I broke it into a bunch of methods, and we'll talk about those. Each of those has a purpose in life. So there's main, yeah. Then there's run scenario, which basically runs a scenario for a certain number of time steps. There's update the space that goes through each logical step. It updates the current space. There's update cell, which updates a specific cell. There's something that computes whether or not this cell should be live given the current state and given the number around it that are live. And then there's something that computes, that counts the number of live cells surrounding it, right? In a certain grid, right? Here, I can ask for a row and column. I didn't actually change this 1D layout. I thought I would show how it could be done even with the 1D layout, although conceptually it's nicer to do as 2D. And so here, basically, I have this way of mapping rows and columns into an index, which can then be used to look into these things. It would be better yet, in terms of cleanliness, to do this at 2D, right? I read the state and write the state as files here, passing in the file name. I ask, okay, is something that's in the file being read in, is that a legal textual encoding? Is that something this program understands what it means in terms of as a string within a space? And if not, I can warn the user. I ask, okay, what is the cell value associated with a given encoding? And I can turn a cell value back into a textual encoding. And that's something that allows me to exit, which is just a built-in function. And then I name something buffer even, buffer odd, which are basically, space that's occupied as the current one during even time steps or odd time steps. And each of these functions is small. It has a very particular job in life. It's a simple job, and therefore it's a testable job. So main reads the states. It runs the scenario here for 999 steps. It could be 100,000 steps, and it writes it out. Quite clear logically what's going on. We read, we run a scenario, we write. Here's run the scenario, and once again, per best practice, we try to keep our functions small. Some authors, prominent software engineers, argue 10 lines is often getting to be a larger function. I'm not very specific about that. There's some inconsistencies, I think, with tabs and spaces. I wasn't careful enough here. Inconsistencies, I should have been much more careful with that when showing this. But basically, it's a small function. Basically, what we do is we go through the steps, and for each step, we update the space. And if it is at a point where it's a reporting step, we print it out, and they will return the latest space. The update the space basically determines which buffer is the current one, which holds the current, which holds the future state, and then it calls, goes through each cell and updates the cell using the appropriate buffers, the current and the next. So this actually determines the next and current. How does it do that? I'd say that these logically, by the unfortunate strictures of C, I am actually using next cells and current cells as here as return values logically of determined current and next cells. Why is that? And let us say if this ampersand before that. What is it? What am I doing there?
You're passing a reference?
I'm passing a reference. I'm passing a pointer to current cells and next cells, okay? Current cells and next cells are int stars. I'm passing a pointer to it, and this thing assigns into that pointer the actual reference to the appropriate arrays to use for the current array and for the next one. So this basically provides a way in C to return more than one return value conceptually. That's functionally what's going on. So we do that by passing in pointers to the things we want it to update, and it will write to them and thereby set them to their appropriate values. Unfortunately, it doesn't directly support multiple return values. Contrast to something like Scala, which does. Okay, so we determine that, and then we go through and we update the cells using the one that was picked and for the appropriate row and column. Each of these, now you can quibble about these, and there's lots to quibble about here. Could you do it better in this other way? Quite possibly this could be significantly improved in one way or the other, but the flow is a lot cleaner. You know, here for update cell, we count the number of cells around it, count the surrounding count of cells. We get the index, we read, we ask is it currently alive, we compute liveness, and we assign that to the new value. Done. Clean. And the names connote what job is being done. Could the names be improved? Yeah, probably, but it's a big improvement. Okay, let's go look at this count surrounding live cells. So basically, what I'm doing is I'm getting rid of this cruft here. Okay, or I'm abstracting it. Both of these conceptually are just variants of that. So here, I'm going through each of the neighboring cells, and I'm doing that with a loop instead of heinously listing it out one after the other. I'm looping through, and basically, if we're dealing with the current cell, delta row, delta call is 0. Just continue on, just go up to the next iteration loop. Otherwise, get the row and column associated with the cell we're looking at. Ask, is this a legal coordinate? In other words, is it out of bounds? If it's not out of bounds, if it is a legal coordinate, then we're going to check is that cell occupied, and if so, we'll count that. Okay? And then we return the number. So those cases have been abstracted into this, and the logical flow is clearer if it's not perfect. We, as software engineers, there's a certain amount of complexity we have to have in our code because it's needed to deal with the situation. What we don't want is to gratuitously add unnecessary complexity, unnecessary cruft that just adds complications to our life. We have a hard enough job as it is. We're being asked to engineer larger and larger, more sophisticated, more fault-tolerant, robust systems that span a large number of platforms. We don't need this in life. Yeah.
I've never seen continue before. What is that?
Oh yeah. Yeah, continue is a construct that you'll find in C-like languages. It figures notably in C++. Java even has continue and break as inherited from the C family. So what continue does is basically it says, if you have a continue, bomb out of this, don't go any further, just go on and go to the next iteration. Okay? So basically it says you're done with this iteration, don't continue on. So
it means loop now.
it says basically, yeah, go on to the next iteration of the loop.
So continue breaks from that iteration and breaks from the loop.
So break will break out of the loop. Continue will go on to the next iteration of the current loop. If I had break here, what would happen is this, because continue, note that we have two nested loops here, and continue is within the innermost of them. So for that reason, when you say continue, it will continue on to the next iteration, the innermost loop, right? If this were break, it would break out of the innermost loop, so it would finish that innermost loop and go on to the next iteration of the outer loop.
It would hit the rightmost bracket and go back up.
That's right. That's right. Yeah. So it would come out of here and go on to the next iteration of that. Okay? Does that make sense? Okay. Each language has its own conventions. It has its own ways of doing things, its own idioms. In 214, you would have seen a few C idioms. If you took 332, you might have been exposed to additional C idioms. C is a language being around since the early 70s with a lot of idioms that have been built up. But in fact, there's different subcommunities who use somewhat different idioms. And there are strongly held sort of aesthetic preferences that different subcommunities have, like including brackets, where brackets are put. There's several different camps as to where brackets are put. There's some that have, if you have an else and if statement, the brackets look like ears around the else. So they'll have, if such and such, and then they'll have a bracket here, and you come down, and then you say else, and you have a bracket here, and these are kind of like ears of the else. Not ears of the elf, but that'll be also nice. But another one would, you have the brackets in here, and the brackets underneath there, and you'll get variants where, the opening bracket is there, and the closing bracket is there. But I'm not really, I don't care that much about it, but having one convention is good because it allows you to look at the code. Having one convention for your project is good. I don't know that there's a particularly inherently better one. I happen to have accorded with one here, but it's not particularly privileged. Anyway, this is some code. Breaking it up into these pieces would allow for unit testing. It would allow for specifications, and we're going to be seeing that, of each of these things that say preconditions, postconditions, things to provide unit tests for these. We could mock these out, like the things to read and write, instead read from a database or write to a database, or just throw the result away, or compute some correctness metric on it, or what have you. But breaking it up into pieces is good, and it allows for an understanding of the overall flow that is much, much clearer than the original code, such as with main. The flow is clear. Other questions related to this? Yes?
Would this be posted on the Moodle?
Yeah. Post this in the middle. Yeah. What do you think the performance cost of this is? We're going to be going into performance considerably with this class. We're going to use profilers to test the performance. Anyone want to hazard a guess? How do you think this code performs compared to the original code?
Exactly the same.
Sorry?
The same.
It's about the same. About the same. What might you, if you were to think about one thing that would give you pause here, what would it be? Like in terms of performance?
Function calls.
Yeah, the function calls. The question is, do the function calls hurt a lot? And students often have a way disproportionate sense of the cost of function calls historically. I don't know if that's true with your particular generation. Function calls are things that are one of the most studied after and sort of thought about areas of performance when it comes to compilers, optimization, architectures. And a lot of time of the engineers, the folks who build the chips and so on, has gone into making function calls cheaper and less burdensome. They serve a key human purpose, yes, absolutely, and allowing us to build better systems. But it turns out their performance cost is modest. It's very, very modest. It's quite small, actually, these days. And in fact, if you were to run this thing with an optimized version of the C compiler, with the C compiler indicating you want optimization, we will be doing this shortly, you would find that basically the cost is in the noise. Okay? It's very, very small associated with it. Amongst other things, an optimizing C compiler will do what to function calls? Yeah.
It will put them in line.
It'll put them in line. So it's as if they're not occurring in the running code, but you really, really benefit by being able to use them because you can get all those benefits of testability, mockability, the ability to sort of generalize many particular cases, the ability to assign different people to write each of these, etc. All those benefits are there, but in the end, often it will end up inlining them. What that means is it will take the definition and it will substitute it in right there. So behind the scenes, if you look at the compiled code, if you look at the assembly language instructions, and you've asked it to put in place optimizations at a strong level, you will see that all expanded in line. Okay. There are some limits to that. And C, what's a case where we can't do effective inlining? Who took 332 perhaps will remember this. Did you have to write interrupt handlers for 332? No? Okay.
They were discouraged from even using functions at all in 332. Like copy and paste everything.
Well, he's right.
Because they're too expensive. See?
Okay, I'm a compiler guy. That's nonsense. So ignore that. Take what you can that's good, but ignore that. Okay? Trust me.
Do you mean DLL files?
Yeah, so with DLLs, where you're loading things in from libraries at runtime, you're not going to be able to inline those because the code's already been compiled. You're loading it at runtime. But actually, in general, pointers to functions. Let's see. Pointers to functions we're going to be using in this course a little bit. There you have a pointer at runtime which points to one function or another. And they're very, very useful methods. They're not nearly as powerful. Not nearly as powerful as closures and forced order functions that we'll see in Scala or Python, for example. But they are very useful. They are also things that need to be treated with respect and caution, much like a chainsaw or heavy equipment. Okay, and when you have a pointer to a function, it's only known at runtime what this points to. This points to function A or function B, and you're not going to be able to inline the call to that because it doesn't know what you're calling. Is it A, B, C, something in another module, and so it's not going to be able to, in general, optimize out that call. But ladies and gentlemen, function calls are going to be pretty much in the noise, and we're going to be showing why in coming classes with use of profiling systems that will allow us to compare the performance of different versions of a program and compare it between languages. So profiler use is one of the big skills that comes out of this class, and we're going to be diving into it shortly. Okay? Okay. Yeah.
I was just going to ask, why do people think that function calls are so expensive? Like just the jump instruction?
No, it's actually more than that. It's a good question, so I welcome that. And there's a history to that, okay? And there's a storied history. I'll write on the board on this side for a bit of equity for the class. So what happens when you make a function call?
Jump in with stuff.
Okay, so there's a call, but there's something more. We have to do something with the stack. What do we do with the stack? So
You have to make a new stack frame.
yeah, we have to make a new stack frame. We have to create what's called an activation record. So let's consider one of these things here. How about this update cell, right? We're gonna go update a cell. Here we're calling off this thing count surrounding live cells. In order for count surrounding live cells to do its job, what does it need to know?
Where it came from,
Where it came from, because it's got to get back there. And what else does it need to know?
instances of all the pass-by values.
Yeah, so all these things that are being passed to it, it needs to know their values, right? It needs to know the value at this pointer pointing to the current cells. It needs to know the current row and the current column. So what needs to happen there is that we have what's called a runtime stack. Okay? It's a set of what are called activation records. Gosh, that was uncomfortable distortion of an activation record. Okay, so we have successive activation records. Let's suppose we're inside update cell here. We're inside the activation record for update cell. In that activation record, we have certain things that are current. Count cells, next cells, row, and call. So count cells, next cells, I'm going to just put them there, row, and call. Okay? And to make this clear, I'm going to put a big bar here. Okay? If we had different colors of chalk, that would be nicer, but that will work. Okay. So those things live on this activation, in this activation record. And in fact, there's more that lives in the stack than just these things. There's actually something called a base pointer and frame pointer, etc. But depending on the language. But when this thing calls off, to count surrounding cells, what's going to happen is it's going to push some things onto the stack, which include the return value, the return where it needs to come back to, the place to which it has to come back. So forgive the poor English. Yeah, it's associated with the return address of the instruction pointer. So it puts some stuff on here, and I'm not going to get into that. That gets down to kind of the low-level computer engineering of it. I'd be glad to talk about that in another class, but I'm not going to now. The key thing is that it also has to push on for this new activation record each of the three parameters, right? So it's, what is it, current cells, and then the row and the call. So here, current cells, row, and call. So it needs to push these onto the stack so that this guy can, or gal, can go and access these things, okay? Can go and get the current column or the current row. And what happens when this one returns?
It passes a value and deletes.
Yeah, so what happens is it's actually going to get, typically the return thing it's returning in C can go into one register, can go into one sort of designated area of fast memory, and then this thing goes away. Boom. Gone. And we're back to this. It goes to the return value and jumps back to it. And it has the return value in the register. It jumps back to the instruction pointer that was pushed. And it's back here, and it continues on in this activation record. And if this calls something else, like if this then calls index for row call, it will then push on index for row call. This is a new activation record, and we'll have row and call, and that will live for a while, and then it will come off. Now, going to your question, which is a really good question, why do people think this is expensive? Back in the day, and this was about the time I was born, okay? About the time I was born, it was said, and I actually never heard this myself, okay? Because I wasn't using computers the day I was born. Yeah. But when you made this sort of call, they actually named it sometimes a thunk. because it would actually make a sound. It was something like that.
All the registers changing in the analog computer.
Well, it was actually and I don't actually know at an electromechanical level why it would make a sound, but it was said that it made a thunk sound. You make calls, and it did take some good resources. I think this is back in the day of probably magnetic core computers. Incidentally, magnetic core. So weird factoid. Weird factoid. You may think I'm singularly weird, but and I wouldn't disagree with that, perhaps. But actually, there's other people in the world who have interests as broad and as extensive as mine, and one of them is Jay Forrester, who unfortunately just passed away. I knew him, and he was a colleague of great significance. He, if anyone was in 394 here, the person who invented magnetic core memory that was the basis for the computers for 15 years or something, which probably was the thing that made these sounds, and which provided the computers, for example, for the space shuttle, which are less subject to cosmic rays. These computers where memory was stored with these little magnetic disks. That person is the same person who invented system dynamics modeling that people would have seen in 394. So stocks and flows, it's the same guy who invented the magnetic cores. And back then, actually undertaking a function call was a fairly expensive thing. It required a number of steps which are expensive there. Now, since that time, computers have sped up by, 100 million times or something. And architectures have been optimized to make function calls much faster. But there is still, among students, there's the occasional injection of delusion that somehow it's a really expensive thing and you got to avoid it. Ladies and gentlemen, if you avoid putting functions in your program, it's penny wise and pound foolish, okay? You're going to spend so much more time debugging your code if it's all one big hairball. You're not going to be able to test it well. You're going to be banging your head against the wall, debugging these memory errors and these problems, that you're going to lose the opportunity to invest your time into things that really matter most. The things that matter these days the most are not piddly little things like function call costs. Those are in the noise these days because of architectural inventions, because of lots of progress in compilers since 40 years ago, and because the things that really hurt us these days, the things that really need investment, are bigger picture things like, is your code parallelizable? Is your code using algorithms, the core algorithms, the things that run many, many times or for long periods of time, are those algorithms well designed? Are they using the appropriate algorithms for the job, or are they unnecessarily expensive? These days, what costs us is also sometimes memory footprint. And ladies and gentlemen, not putting your code into functions is likely to really blow up the amount of space occupied by your code, because you've got repetition of code in many places. And actually, if you have functions, when you call them, you will probably hit the cache or hit faster memory, and as a result, it will run faster than if you had that code just sort of splayed out in many places. So these days, when we talk about optimizing systems, the things that matter are often far deeper things than just whether or not you have function call boundaries. Should you have those? Yes. If you don't, you will spend your time, the opportunity cost will be huge. You'll be spending your time trying to micro-optimize this thing which is in the noise. It doesn't really matter for performance, and you'll be sacrificing the things that really do, which is putting that same time you could have invested it in algorithmic improvement and parallelizing your code and improving that code to have a smaller memory footprint or what have you. Those are the things these days which matter. And the people who get caught up in, small things like avoiding function calls because they think they're going to somehow save time. It's delusional, and it is something which is going to cause needless waste of opportunities for speeding up your programs. So I'll get down now off the pulpit with fire and brimstone. Okay, code. This is code. Cleaned up some. It could be cleaned up further. You notice I also abstracted out this rule for compute liveness. We're going to come back to this. We're going to allow for multiple rules for compute liveness. And we're going to dictate which of them we'll use through pointers to functions. Okay? And we're going to see the effect of optimizing this. Okay, bit of code. I'll post it. Okay? Great. Any final questions about that before I use the remaining time to push forward a little bit of conceptual discussion? Yes.
Me?
Yes.
For the implementation of compute liveness, you're still sticking with the greater than equal to 2 and less than equal to 3.
Yeah.
I'm not sure why that is. 'Cause
Here.
yeah.
Because these are, first of all, great question. Great question. I welcome this. So the first thing is that so the question is, why don't I abstract those into constants which are sitting up at the top, for example, right? They only appear once each in the program. This 3 is logically distinct from this 3, actually.
I think it's why aren't you using double equals?
Yeah, that was my question.
Why am I using double equals?
Why aren't you?
Why isn't just equal 2 or 3?
Yeah.
Oh, I see. You could say, does this equal 3, or does it equal 2, or does it equal 3?
Yeah.
I could have done that. Conceptually, I think of it as the cells have to be within a certain range. The count of cells surrounding you have to be at a certain range. Right here, it's a very narrow range, 2 to 3. But as you'll see, we'll be looking at variants of this rule which allow broader ranges. And so the way I was thinking about this conceptually was that this is some tolerance, some range of possible values under which it would remain alive. And so I treat it as kind of a range by saying, is it greater than or equal to this, or less than or equal to that? I could have said, is it equal to this or equal to that? But I anticipate generalizations of this rule where it's not just 2 possible values, it's many, and it's really allowing them in a range. So that's why I put that in there. You could argue if this were the only rule you were considering, maybe that would be a bit clearer. I also happen to think, and this gets into the psychology of programming and in fact debugging, so ladies and gentlemen, we live in software engineering and software development. We live in a human theater. And for those of you in 371, we'll be learning a lot about that human theater this semester, both in the classroom and out. But beyond that, there's a lot of decisions we make as software engineers. If we're careful, if we're meticulous, and we're considered in what we put down, there's things that consider limitations of human reasoning. And one of the things is you don't have double negatives. So when you create a function, you don't want it to be you don't want the function to be is not this. Because people are poor at reasoning about negatives, and they're terrible about reasoning about double negatives. Like if it's not that, then it is that. People are just poor at reasoning about these things. And if it's late night and you're trying to track down a bug, you don't want to leave your code vulnerable to that sort of mistaken reasoning or complicate the situation unnecessarily. I think ands are sometimes a little bit easier for people to reason about, say this condition and this condition, because it allows us to decompose it. Okay, I fault my statement here, but it allows us to say, okay, is this true? If that's not true, we're done. If this one true, if that's not true, we're done. But you could argue or. I mean, I don't know. I'd probably take that back, but I prefer to think in terms of ands when it's an option, so I like doing it that way, and I think it's a little bit simpler to reason about. Where it gets a little bit messier is when you have combinations of ands and ors, and I think they're sort of a preference for dealing with sort of ands and conditions is sometimes a little bit easier to reason about. Not really satisfactory answer, but we're going to take, the important thing is, why didn't I put these into constants? I mean, that's an interesting question. I didn't put them into constants because they appear once and they're specific to this rule. And I don't want to litter my space of things up there with things that are only used once and that are unlikely to be ever reused. I want, those are specific to this rule, there's no use defining them as constant. That wasn't your question, but that's an important principle. It's not like I'm saying exterminate all constants from your program. I'm not advocating here, Jeremiah, a sort of attempt to wipe out constants from your program, put them all, by fiat as Pound defines. That's not my point at all. My point is, don't leave yourself vulnerable to change by having several things that are logically the same disconnected, because if you do that, you might update 3 of them and forget to correct the 4th. Things that are repeated, things that are likely to change, those are the things that we often associate with Pound defines. Does that make sense? It's a pragmatic thing. This is not about checking boxes. This is about protecting ourselves as software engineers. It's about hygiene. It's about practicalities. Okay, other questions?
Did you leave the arrays as global variables, or did you?
I left them as global variables because they are used across multiple functions and because they are a central sort of data structure in this that is assumed. And I could be faulted at that, but you'll notice something that I did that was that mitigated that. I left these here because where could these have lived? They could have lived inside main. What would that mean? What would that mean in terms of activation records? If you had an array inside main, and we were to consider main's activation record, what if I had one of these big arrays inside main? What will happen when we enter main? It's actually going to be really big. It's going to, when it enters main, it's going to push on a really big array. It's going to actually allocate the space for a big array. But that's not a big problem. I could have done it. I could have made them specific to main, and maybe that would have been the right idea. So when I enter main, I could have had those on the stack. These would be giant, arrays instead of just these small things, and they'd be popped off when I left main. I could have done it. Note what I did though. Where are these things referenced in the code? Where are these things referenced? How many places? There and there. So basically, they're declared here, defined here. We're reading into them, and then here we're determining which buffer we're going to use for the current time step. Okay? Determine next to current cells. Really should say for current time step or something. But the point is we're figuring out which of them to use. You'll notice that the things that actually used them originally, I mean this code here, A and B and all that sort of gunk, those things are in fact not directly, the corresponding code is not in fact directly referring to the underlying global variables. So, for example, this one here, count surrounding live cells. You notice that this is passed in as a pointer. So basically what happens is I declare these as globals, I read into them, and then I basically run the scenario and get the final state from that. And within run scenario, basically what's happening is that I am updating the space, and for the space update, I'm determining which are the current cells, which are the next cells, and using those appropriately. Within this call, this is the place that actually refers to those variables. Write down, come on, get me, there it is. This is the place that refers to those global variables, but it's all encapsulated. In other words, I call off to that, I determine which are the appropriate things that are for the current cells or for the next cells, and right there, and then I am using them here. I'm not actually referring to those global variables. So I basically really encapsulated the things that have to refer to the global variables to just one or two places. Could I have passed them down for main? Yeah. Given that I've limited the references to them to just two places, one to pick which is current and which is next, and one to read it in to the appropriate one. They could be global. We don't lose a lot of sleep because of it. We don't have things accessing them globally. So could they have been a main? Yeah. Maybe that would have improved it slightly. I'm not averse to that. I think maybe that would improve it slightly. But it's really a small potatoes because we don't refer to them in a promiscuous way. The problem with global variables, ladies and gentlemen, is general. It's not that we have to, it's not inherent in them. Ladies and gentlemen, the problem with global variables is that they are confusing because lots of places in the program might refer to them and we don't know which place does. When their use is confined, circumscribed to just a small number of places that are clearly delineated, the risks associated with global variables diminish hugely. The problem, as Shakespeare said, lies not in our stars, but in ourselves. How we use these things. Just like constants, they're not to be exterminated, but they're to be used consciously and in a way that's careful, that's heedful. So it is with global variables. We don't want to get rid of them. We want to use them in ways that avoid putting big vulnerabilities in place, that leave us open to abuse and problems. And it's not a bad idea to eliminate them if possible, but if you're going to have them, you have them in a way that limits their risks. Okay? Other questions? Okay, so ladies and gentlemen, time is a close in here. So I had asked you to install Scala, a programming language called Scala. And I got some questions from one or two students about Scala. Should I use the Scala IDE? What variant of this? Basically, ladies and gentlemen, what I want you to be able to do is to be able to fire up Scala on the command line, because that's what we're going to be doing. So let me go show this to you. And I do it, ladies and gentlemen, with no small measure of delight. Okay? So here's my console. Okay. Maybe I should make this larger. Here we go. Oh man. Enlarge font. Okay. Control. Boom. How's that? Good or not? Okay. Spark. Oh, not Spark Shell. Sorry. Some of my students know why I'm laughing. Okay. Scala. Here we go. Okay. Here's Scala. This is the Scala REPL. What do I mean by the REPL? Anyone? Read eval print loop. This is going to be what we're going to be using to program things in Scala. And I don't care if you install an IDE. I think that'll be fine. It might be an asset for some of the assignments that use it. And you might want to use it even for some of the take-home exercises. But the main thing we need, and the thing that would be sufficient for most of it, is this. You actually won't need an IDE for most of the things, although it wouldn't hurt for some things, but there'll be alternatives with SBT, etc., the Scala build tool. So val foo equals 1 here, and we could def sum. And we could have, x being an integer, y being an integer, and this is equal to x plus y. So this is what we'll be using, and this is what I'd like you to have at your disposal. So as long as you have something that allows you to launch the Scala REPL, install a command line tool, that will be fine. Now, some people have used, I think Aiden used to good effect, and Anahita as well. You used a tool that provides a command line interface, but it's within an editor, right? And that was, what was it called? It was like some sort of gem, sapphire, or what is it? Sublime. It was Sublime. Thank you. It wasn't a gem. It was something more beautiful than a gem. It's something sublime. So you might want to use Sublime. Okay. That would also be fine. The key is to be able to use the editor. We'll be using it next time. Yeah.
I'm going to take a guess that this also works in Ubuntu. So if you have Windows 10, you can install Ubuntu inside it, because that's the thing now. You can install Bash.
Yes, that's right. So that would be fine. But it also, I think there's a Windows version of it that can work from the command line too. So that'd also be fine. But absolutely. So this is Ubuntu. Okay, ladies and gentlemen, thank you. Thank you for coming here on such a cold day and during the career fair. Please make use of the career fair, and I will see you on Tuesday.